Okay, in this video, we're going to talk about section 2.4 dealing with infinite limits. And in this section, pretty much we'll deal with infinite limits. We'll look at some of the definition of infinite limits and how to deal with, how to find those. Also, we'll look at one-sided limits. And also we'll do a lot of, well, just a few examples there. Also, we're going to be finding infinite limits analytically. Okay, so that's just the basis of section 2.4. All right, so here we got two or more limit scenarios are frequently encountered in calculus and are discussed in this and the following sections. An infinite limit occurs when function values increase or decrease without bound near a point. The other type of limit, known as a limit at infinity, it occurs when the independent variable x increases or decreases without bound. The ideas behind infinite limits and limits at infinity are quite different. Therefore, it is important to distinguish these limits and the methods used to calculate them. Okay, so here we're going to look at a general picture of these two limit scenarios. And this occurs with the same function here. All right, so the one we'll talk about is an infinite limit in this section. And with an infinite limit, when you have a graph of a function, what's happening here is that the y value is going to be approaching infinity as x approaches some value of a. So as x approaches some value of a, what's going to happen here is that your y will be going to infinity. It's not going to go to a definite or just a definite y value. It's just going to be off to infinity. And these two deal with limits at infinity. What's happening here is this. As we let x get bigger and bigger and bigger, the bigger x gets, then what's happening here is that this function will be approaching positive infinity. Well, y is going to be approaching some value of m. It'll never get to m. It probably won't get to m, but it's getting closer and closer to m as we let x go off to infinity. Now, if we let x go up to negative infinity, that means that we let x get smaller and smaller and smaller, that's negative infinity, then the graph of y gets closer and closer to some value of L. It will never reach L. It might not reach L, but it'll get closer and closer to L. All right, here's a definition of infinite limits. Suppose f is defined for all x near a. If f of x grows arbitrarily large for all x sufficiently close but not equal to a, then we write it like this. The limit as x approaches a of f of x equaling to infinity. And that's in this case positive infinity. And if f of x is negative and grows arbitrarily large in magnitude for all x sufficiently close but not equal to a, we write it like this. The limit as x approaches a of f of x is equal to negative infinity. Okay. Now, in both cases, the limit does not exist, as indicated here. However, we'll have to, when we write our answers, we'll usually say either positive infinity or negative infinity, okay? And the reason why they're saying that the limit does not exist, because usually a limit, when you're dealing with a limit, you're trying to find out the value that the function will be getting closer and closer to as you let x approach some value, some number, okay? And negative infinity and positive infinity usually are not exact numbers, Okay. All right, on the next page, well, here's some examples of that. Here we're going to let x approach a. Here's a, going in both directions from the left and from the right. So that means that your f of x, this function y equal f of x, is going to be getting arbitrarily large. Okay, it's not going to some finite number. It's just getting arbitrarily large. And on this figure right here on the right, if we let x approach a, then here this graph of y equal f of x will get arbitrarily large in magnitude. So here f of x is negative and it grows arbitrarily large in magnitude. Okay. Now back to one-sided limits. Suppose f is defined for all x near a with x greater than a. If f of x becomes arbitrarily large for all x sufficiently close to a, with x being greater than a, then that means we can write that as the limit as x approaches a from the right of the function f of x equaling to infinity, okay? That's this figure right here. No. Now the one-sided limits, one-sided infinite limits would be this. The limit as x approaches a from the right of f of x is negative infinity. The limit as x approaches a from the left of f of x will be infinity, and the limit as x approaches a from the left of f of x is negative infinity. Those are defined analogous. Okay. And unfortunately, I do not have those figures here for this definition for you to see for those one-sided limits. Okay. All right, the line x equals a is called a vertical asymptote. It is a vertical line that is approached by the graph f as x approaches a. Okay. If you remember back in college algebra, we did talk about what vertical asymptotes were when you were graphing a rational function. Usually a vertical asymptote is just a vertical dotted line going through the x-axis at some value a. Okay. And here's that definition using calculus, using limits. If the limit as x approaches a of f of x is equal to plus or minus infinity, and that's going to be from the left, well, just that, just a limit as x approaches a, and then the limit as x approaches a from the right of f of x equals to plus or minus infinity, or the limit as x approaches a from the left of f of x is equal to plus or minus infinity, we can say that the line x equals a is called a vertical asymptote of the function f. Okay. All right, now let's start off with example 1. In this case, we're going to compute the values of f of x is equal to x minus 6 divided by x minus 1 quantity squared in the table to the right and use them to determine the limit as x approaches 1. Okay, so we're going to use this table down here. Okay, and also we're going to use our TI-84 calculator to do this. All right, so in the calculator, what I'm going to do here is go to y equal to, and you might need to clear out any equations that you may have in y1, y2, and so on. Now, the numerator and the denominator, pretty much we're going to put in parentheses. So for the x minus 6, I'm going to use left parentheses, xt theta for the x minus 6, close parentheses. That's going to be divided by the denominator, where that x minus 1 quantity squared needs to be in parentheses. So it'll be left parentheses, x minus 1, close parentheses, and then hit x squared to square it. Okay, so that's the equation in y1. Okay, now I'm going to go to second window. I want to make sure for the independent variable, ask is highlighted. If it's not, you might need to use the down arrow key to independent, use your right arrow key to put the cursor above the word ask, and then hit enter. Because what you want to do here is have the calculator ask you what values of x you're going to put in. And these are the ones you're going to type in to get your y value. So here I'm going to do second and graph. Let's see, I'm going to delete all these numbers out. And then we're going to start with, in this case here, 1.1. So for x is 1.1, that's going to be negative 490. And then for 1.01, and then hit enter, we get negative 49,900. And then for 1.001, now you might get a number in scientific notation, but what you can do here is use the up arrow key to highlight that x value, and then use the right arrow key to highlight y1 for x equal 1.001. And at the bottom, you'll see the exact value, negative 4,999,000. So this is negative 4,999,000. And then finally for 1.01, I'm going to use my down arrow key and then go back to x1, go back to the x column and type in 1.0001. Then go back up and then use your right arrow key. You'll see what that value is. It's negative 4 with 4 9s and 4 zeros. So that's actually negative 499,990,000. So with this one, you can see that these numbers are getting arbitrarily smaller and smaller and smaller as we let x approach 1. And actually, it's going to be approaching 1 from the right because these numbers are bigger than 1. So this represents a limit as x approaches 1 from the right of 1 of that function f of x. It's getting smaller and smaller and smaller without n. So it will be negative infinity. Okay? Because as we let x approach 1 from the right, what's happening here that these values of f of x are approaching a precise number. It's just getting arbitrarily small. So that means negative infinity. All right, now for this one, the 0.9, 0.999, 0.999, and 0.9999, that's going to be the limit as x approaches 1 from the left, because those values are to the left of 1. Okay, so now let's go back. Position this in the x column and type in 0.9. See what that's equal to. And in this case, it's going to be negative 510. And then for 0.99, that's going to be negative 50,100. Okay, and then for 0.999, okay, let me go here and then put that cursor over the number in y1 because it's in scientific notation. This will be your y value, negative 5,001,000. Okay, and under x 0.9999, back up here, It'll be this number, -5, -500,000, -500,000,000, 10,000. Okay. So you can also see here, this is not approaching some number. It's just getting smaller and smaller and smaller. So the limit as x approaches 1 from the left of that function f of x would be also -infinity. Now notice from the left of 1, the limit approaches -infinity, and from the right of 1, the limit approaches also -infinity. So that means that the limit as x approaches 1 of f of x will be -infinity. Because from the left and from the right, f of x is the values of f of x as we let x approach 1 will be getting smaller and smaller and smaller. -infinity. All right, number 2. Second example looks like this. Here we got a graph. And we're going to use that graph to determine the indicated limit if f of x exists. So here I want to find the limit as x approaches 1. Well, by looking at this, if I go to the left of 1, here's 1 right here. To the left of 1, it's going in a downward direction without end. So that means that's going to be -infinity. And if I look at 1 from the right, that means that these values are also going downward without end. Both are approaching -infinity. So the limit as x approaches 1 of f of x is -infinity. Okay. Because if you look at the left of 1, the limit as x approaches 1 from the left, that's -infinity. And the limit as x approaches 1 from the right of that also goes to -infinity. Okay. Okay. All right, let's look at this next example here. This is the graph of f of x shown below. It has a vertical asymptote at x equals 3 and x is equal to 6. So here you can see those 2 vertical dotted lines here, each crossing the x-axis. One is at 3 and the other one is at 6. We're going to use those graphs to find the following limits. Use infinity or -infinity where appropriate. So starting with part A, I want to find the limit as x approaches 3 from the left of f of x. So here's 3 right here. That's where the vertical dotted line is at. Let's find out what's happening on the left of 3. So to the left of 3, you're going to see that it's going downward without end. It's actually going to be approaching -infinity. Okay. So the limit as x approaches 3 from the left of the function f of x is -infinity. Part B, the limit as x approaches 3 from the right of the function f of x. Well, here's 3. Let's look at what's going on to the right of 3. Here, this is going in the upward direction without end. So that means it's approaching +infinity. So the limit as x approaches 3 from the right of that function is going to be +infinity. Now part C, the limit as x approaches 3 of f of x. Okay, so for the limit, we need to look at what's happening on the left and on the right of 3. They have to approach to the same place. Here, from the left of 3, the limit is going to negative infinity. On the right of 3, the limit of f of x is going to positive infinity. Those are going to 2 different directions here, 2 different places. So the limit as x approaches 3 of this function does not exist. I'm using DNE for does not exist. All right, now part D. Say we have the limit as x approaches 6 from the left of the function f of x. The limit as x approaches 6 from the left of f of x. In this case here, here's 6 right here. On the left of 6 is going upward to infinity. Okay, without n, it's just going upward to infinity. So the limit as x approaches 6 from the left of that function f of x is infinity. Now part E is the limit as x approaches 6 from the right of f of x. But here's 6. Let's look at what's going on to the right of 6. Here is going upward to positive infinity without n. So the limit as x approaches 6 from the right of the function f of x is infinity. And part F, so you have the limit as x approaches 6 of the function f of x. Well, from the left of 6 is going to infinity, and from the right of 6, the limit of the function goes to infinity. So they're going to the same place, infinity. So that means the limit as x approaches 6 of f of x is infinity. Okay. All right, and here's, let's say one more example of this right here. The graph of f shown below has vertical asymptotes at x is equal to -4 and x equal 5. Find the following limits. Use infinity or negative infinity where appropriate. So in this case here, let's look at the limit in part A. The limit as x approaches 4 from the left. The limit as x approaches actually -4 from the left of f of x. And in this case here, here's -4 right here. To the left of 4, this is going upward, getting closer and closer to that vertical asymptote. So it's just going upward, excuse me, it's going upward to infinity. So the limit as x approaches 4 from the left of f of x is infinity. Part B is the limit as x approaches -4 from the right of f of x. And in this case here, to the right of 4, here's right of -4 is -4. To the right of that is also going upward to infinity without end or without bound. So the limit as x approaches -4 from the right of that function f of x is infinity. Okay, and now part C is the limit as x approaches -4 itself of f of x. Well, to the left of -4, the limit is going to infinity. And to the right of -4, that limit is also going to infinity. So the limit as x approaches -4 of f of x is infinity. Okay. Part D. The limit as x approaches 5 from the left of the function f of x. Well, here's 5 right here. Let's find out what's going on to the left of 5. Here is going downward without bound. It's getting smaller and smaller and smaller without bound. So that means the limit as x approaches 5 from the left of f of x is negative infinity. And then part E is the limit as x approaches 5 from the right of f of x. Well, here's 5 right here. If we come from the left of 5, from the right of 5, it's going upward to positive infinity. So the limit as x approaches 5 from the right of f of x is positive infinity. And then part F is the limit as x approaches 5 of f of x. All right, notice here, from the left of 5, the function approaches negative, the limit of the function approaches negative infinity, but to the right of 5, the limit of the function approaches positive infinity. It's going to two different directions, two different places. So that means that the limit as x approaches 5 of f of x does not exist. Does not exist. Okay. That's how we use graphs to find to deal with infinite limits. Okay, now let's find infinite limits analytically. Many infinite limits are analyzed using a simple arithmetic property. The fraction a over b grows arbitrarily large in magnitude if b approaches 0 while a remains non-zero and relatively constant. Okay. Now with this, let's look at example 5 here. Okay, we're going to try to deal with this one analytically, like finding the limits in a through c below for the function f of x equal to x squared minus 8x plus 7 divided by x plus 7. And we're going to be using negative infinity and infinity when appropriate. Let's look at part A. We're finding the limit as x approaches negative 7 from the left of the function f of x. All right. So let's try to analyze this. We got the limit as x approaches negative 7 from the left, and my f of x is x squared minus 8x plus 7, all divided by x plus 7. Now, I'm going to analyze the numerator and the denominator. The numerator, of course, if I replace the x with negative 7, this one I'm going to have negative 7, that's squared, minus 8 times negative 7 plus 7. Square the negative 7 will be 49, minus 8 times 7 will be plus 56, and then plus 7. And if I add 49, 56, and 7 together, I'm going to get 112. Okay. Now for the denominator, I know at 0, I know at negative 7, I'm going to get a 0 on the denominator. But I need to look at what is going to be happening if I approach negative 7 from the left for the x plus 7. Okay. Now, if you recall, if you want to, you can draw a number line. And we'll deal with negative 7 here. Negative 7 coming from the left. That means I'm gonna have negative values that are less than -7, like -8, -7.5, -7.2, -7.1. But those values, if I add that to -7, I'm going to get a negative value. That means this will be negative, but it will be getting closer and closer to 0. It'll be approaching 0. So that'd be negative there. Okay. It's negative, but it's going to be approaching 0. So that means if I take the limit as x approaches -7 from the left of that function f of x, it's going to get closer. It's going to get to -infinity, because the denominator will be negative, but it will be getting closer and closer to 0 if we go negative. Now, part B, we got the limit as x approaches 7 from the right of f of x. So here the limit as x approaches 7 from the right of course, x squared minus 8x plus 7, all divided by x plus 7. Well, that numerator, I've already evaluated that as 112 when I replace the x with 7. But let's look at what's going on when we approach -7 from the right. That's going to be coming in this direction to the right. It's going to be values like -6. Let's say -6 or -6.3, -6.5, -6.8. But whatever value I choose there, anything like -6 or -6.5 added to 7 is going to end up being positive. In other words, it's going to be positive and approaching 0. Positive and approaching 0. So in this case, here the limit as x approaches -7 from the right of that function would be, in this case, positive infinity. Now in part C, if I want to find the limit as x approaches -7 of that function, here from the left of -7, the limit of the function goes to -infinity. And as we approach -7 from the right, the limit of the function goes to infinity. It's going to two different places. So that means that the limit as x approaches -7 of that function does not exist. Okay. And sometimes if you type that function into the calculator, you might see what's going on here. Like, let's see here, in the numerator, x squared minus 8x plus 7, and that's in parentheses, divided by, and then left parentheses, x plus 7. And then I'm going to hit zoom 6 for the standard window. Okay. Or I might do zoom fit. I'm gonna try. Let's see if that works. Yeah. Because here the vertical asymptote is at -7. And as you can see, on the left of 7 is going to -infinity, and on to the right of 7 is approaching positive infinity. Okay. So that's why in this case, the limit does not exist. Okay. Okay, here's example 6. Let's say I want to determine the following limit or state that it does not exist. And in this case, you've got the limit as x approaches 1 of 4x squared minus 4 divided by x squared minus 1. Okay, now what I would do is work this particular problem the same way I would if I needed to use a technique for computing limits. Okay, if I use direct substitution, I would get a 0 in the denominator, so that would not work. However, if I try to factor and divide out any common factors, that may help. And I'm going to try to do so here. So if I bring over the limit as x approaches 1, in the numerator, there is a common factor, which is 4, in 4x squared and 4. So I factor out the 4. 4x squared divided by 4 will be x squared, minus 4 divided by itself will be 1. All that's divided by x minus 1. Okay. Now, I'm going to bring down the limit as x approaches 1. That x squared minus 1 is a difference of 2 squares. So if I bring down the 4, I can factor that x squared minus 1 into 2 binomials. X squared breaks up as x and x. 1 would be 1 times 1. It is a difference of squares, so one has to be plus, the other one has to be minus. And then all that's divided by x minus 1. And notice I can divide out the common factors here. I can divide out that x minus 1. So that means I'm left with a limit as x approaches 1 of 4 times the quantity x plus 1. And in this case, now I've reduced this to a polynomial, which I can use direct substitution. Okay. I can go in and substitute the 1 in for x, so that'll be 4 times 1 plus 1. 1 plus 1 is 2. 4 times 2 is 8. So the limit as x approaches 1 of 4x squared minus 4 divided by x minus 1 will end up being 8. Okay. All right. And on the last page of your handout is the last example for this video. Here we're going to use analytical methods and or a graphing utility to identify the vertical asymptotes, if any, of the following function. In this case, here we got f of x is equal to x squared minus 9x plus 20 divided by x to the 12th minus 5x to the 11th. Okay, now first of all, before you find out what your vertical asymptotes are, you need to see if you can divide out any common factors. And in this case, we can divide common factors out. Like x squared minus 9x plus 20. That can be factored into 2 binomials here. X squared breaks up as x and x. Now I need factors of 20 that will give me a middle term of negative 9x. That will have to be 4 and 5. And they both have to be negative since the middle term is negative and the last term is positive. That's going to be divided by, now for the x to the 12th minus 5x to the 11th, I can take out a common factor there, which is going to be x to the 11th. X is in both of them, so if you're going to factor something out, you take out the common variable with the smallest exponent. In this case, I use x to the 11th. So now x to the 12th divided by x to the 11th would just be x. And then minus 5x to the 11th divided by x to the 11th would be 5. All right, and in this case here, I can divide out common factors here, which is the x minus 5. They're gone. So I'm left with x minus 4 divided by x to the 11th. Okay. And now I can find out what my vertical asymptotes are by taking the denominator of x minus x to the 11th, set that equal to 0, and solve for x. Well, the opposite of something to the 11th power would have to be to take the 11th root on both sides. And there's no need for the plus or minus symbol because that exponent is odd. So the x is equal to the 11th root of 0 is 0. So that x equals 0, that is your vertical asymptote. That's going to be the vertical dotted line that crosses the x-axis at 0, which is actually, in this case, going to be the y-axis if you look at it. I'm going to try to enter this in the calculator so that you can see what that graph looks like, if at all possible. I'm going to clear this out. Now I do left parentheses x squared minus 9x plus 20, close parentheses, divided by left parentheses x, hit the hat key and then 12, use your right arrow key to get out of it, minus 5x, hat key, 11. Right arrow, close parentheses. Now I'm using the standard window. Okay. Or I can do this, zoom in. Let's see if I can get a better look at this. Okay. Well, I might need to zoom out just a little bit because okay, but pretty much you can get the idea that your vertical asymptote is here. And of course, on the left of 0 is going to be going off to positive infinity, and to the right of 0 is going to be going off to negative infinity. Okay. So that's what that graph looks like. Okay, so that will conclude this video in section 2.4 dealing with infinite limits. Feel free to contact me if you have any questions about anything presented in this video or any of the homework problems that are in my math lab.